going to do a Praxis review on algebra. And if you don't know, there is an application that you can use that will help you with the technology on your test. So you've already taken the Praxis, and you know that they have a calculator on there for you. And if you want to be more familiar with it, you can go to this website right here, infinitys.com/exams/tutorials, and it will show you what the computer has as a calculator for you and how to use the scientific and the graphing calculator on there. So if you take a look at that PowerPoint, you can find this on there on that first slide once you put it in play mode.
Okay.
So the first thing I want to do is briefly just talk about some stuff that's really easy and just kind of get us warmed up. With this particular inequality, what we're dealing with is something that's linear. And so what I'd like for you to do is not just think of it algebraically, but also think of it from a graphical standpoint. Does that make sense?
Yeah.
So you're thinking of the function 1/2 x plus a half. When is it greater than 1/4 x plus a third?
Yeah.
And so that'd be a visual way of doing it. Obviously, you can multiply everything by 12, get a common denominator, and then solve for it, right?
Mm-hmm.
Okay, so I'm not doing that one. But what does this mean?
Well, you work from the inside out, right?
Okay, so it can, that's if you're thinking of it algebraically. What if you're thinking about it functionally?
When is the function 2x plus 5/3 greater than -3 but less than or equal to 5?
That's right. So I'm going to now bring us back to a picture of me. So here's that particular inequality, right?
Mm-hmm.
And if you're graphing that, then we're thinking down here is -3. And up top, we have a solid, and that's 5.
Mm-hmm.
And so we're looking at 2/3 x plus 5/3. So we find our y-intercept, and we graph that little booger. And we're trying to find out when it's trapped in between there.
Mm-hmm.
So anyways, I think that's pretty elementary for us to think about. But nevertheless, sometimes it's helpful to have a graphical image of things of that nature to work these problems.
Yep.
So I don't know if you want me to go ahead and work the rest of that out or not.
Oh, no, that's fine. You can keep going.
Okay. I didn't think that you wanted me to do that. Okay, so now here's our next section, solving inequalities algebraically and graphically. And so we have this wonderful quadratic that's equal to 0. Mm-hmm. And we have the nice little hint or reminder that if you have two things multiplied times each other and it's equal to 0, that tells us that one of those factors has to be equal to 0.
Mm-hmm.
So let's take a look at this particular function. And how would you solve that one?
I would do first times last to get 4, and then I would find all the factors of 4 that would give me -3.
Okay, so you would do some type of factoring.
Mm-hmm. Yeah.
That'd be one way of doing it. So let's see if we can do that together. So we have 2x squared minus 3x minus 2, and that's equal to 0. And you were wanting to look at, what did you say, the first times the last?
Uh-huh.
Okay,
yep.
So you're looking at the lead coefficient.
Oh, yeah.
And you want to find factors of 4 that then sum to -3.
Yep.
And in fact, what we're really looking for is factors of -4.
Yeah.
Okay, so, and what we're doing is then we're going to make a substitution for our linear term.
Mm-hmm.
All right. You satisfied with that?
Yep.
So we factor out a little 2x action on the first two terms. And the way that this always works is whatever's in this parentheses will be the same there. So now those guys are friends. We're going to factor them out. And what's left is this right here. So that tells us that this is either equal to 0 or the other one's equal to 0. So x is equal to 2, or 2x is equal to -1, which means that we have that. So.
Okay, so what if you're trying to find the zeros or factor like a polynomial that's greater than degree 2?
Okay. Yeah, so if we have a cubic or of something of that nature.
Yeah, or even up to 6 or whatever. Because they had a few of those on there last time I took it, and I was trying to do that third step down there from the top, and because I've never seen that look like that. I've did the first times the last, and then I'd find my two factors. I'd get my 3 or I'd get 4 and 1, and then I'd put my 2x on one side, then I'd put x on the other side in separate parentheses down there on your.
Okay. Yeah. So what I'm doing is I'm factoring by grouping.
Yeah, I've never seen it like executed like that, and that's probably what hung me up whenever I was trying to group my things together.
Yeah. So in this case, these first two terms right here, I'm going to group them together and factor out whatever's in common.
Mm-hmm.
And then what's in this parentheses, if it's factorable, will have to be the same that's what's over here. So then I group those together, and there's nothing in common save 1. And so I'm just reversing the distributive property.
Okay.
Just so that you'll get a better glimpse of this, if you're thinking of this as an area model, what we've just done is we've said that this is x, and that's -2. And this is 2x, and that's 1. Does that make sense?
Mm-hmm. Yep.
And so there, in fact, is your 2x squared. There's your x. There's your -4x, and there's your -2.
Okay.
And so we were factoring out what these guys have in common.
Oh, okay.
Does that make sense?
Yeah. Yeah, that actually makes it a lot better. Now I can actually see what's going on here.
Okay. So that'd be one little doodad that we can work with. Let's see. Oh boy. What does this mean to you?
Extracting square roots.
I mean, when you see that, well, what are the first things that come to your mind of how to solve that?
The first thing I would do, I would try to expand the left side.
Okay. And then what?
And then I would subtract 9 from the right side to make it where it equals 0. And then factor from there.
All right, so there's nothing immoral with doing it that way.
Yeah, I know that's the long way, but
it's what you're comfortable with, right?
Yeah.
And once you do that, then you can perform I don't know, the quadratic formula.
Mm-hmm.
And that's fine. I'm not going to do it that way.
Okay.
Let's see. this is something squared, right?
Yep.
And then it's equal to 9. So you know it's quadratic. Does that make sense?
Yep.
So whatever this thing looks like, it's quadratic, it opens up, and I'm telling you that this quadratic happens to intersect at 9. And so I'm trying to find out what those two values are, or one value, or no values are.
Mm-hmm.
Does that make sense?
Yeah.
Okay. In fact, the instructions told us to solve this algebraically, but I'm just giving you a visual that we could potentially have two answers on this one. And I just always think it's helpful to have another representation. Okay, so what I'm going to do over here is, because I have something squared equal to 9, I also know that 9 is the same thing as 3 squared.
Yep.
Okay, so now what's going through your head?
Take the square root of both sides.
Okay, so if I take the square root of both sides, that's just going to give me the positive one, but we know that there's a positive and a negative root, right?
Mm-hmm.
Okay, so I'm going to have 2x minus 1, and that's going to give me plus or minus 3.
Yep.
And now we can start solving in some conventional way, where we have 2x is equal to 1 plus or minus 3, and then divide all that by 2.
Mm-hmm.
So that'll give us our answers for that one.
Yeah.
And oh boy, you remember how to complete the squares?
No.
No. Okay, so this is going to be good for you, because sometimes you may forget the quadratic formula, right? I mean, that's possible. I forget it all the time. And if we remember how to complete the squares, we can actually derive the quadratic formula. And now, if you're noticing on that little cheat right there, it says to complete the square, we have x squared plus bx, and it's equal to c. But what we're given is not necessarily in that form. And this one is slightly different. And all right. So the first thing that I'd like to do on this is to isolate the quadratic and the linear term on one side, and make sure that the quadratic coefficient is 1.
Okay.
So in doing that, I will have x squared minus 5x is equal to negative 17 fourths. So far, so good?
Yep.
Okay. So when we have a perfect square, we know that this is 2 times whatever whatever's been squared here and whatever's going to be squared there. And so we'll take this guy right here and we'll half it and square it. But I can't just add it on that side, can I?
No, you gotta do it on the other side too. So this
this on the left-hand side now happens to be a perfect square. Everyone's super elated. And let's see, what's going to happen on the other side? I have negative 17 fourths. And then I'm going to also have 25 fourths.
Mm-hmm.
So when I deal with all of that, is that 8 fourths?
Yeah.
Did I do the math right?
Yeah, I think
Okay.
so.
I mean, you've been up in front of people all week long, right?
Yeah.
Got to do this stuff on your feet. Okay, so, and that's the same thing as 2. And now we're back to where we were earlier, right?
Yep.
We've seen this. Take the square root of both sides.
Yeah.
And when we do that, we're going to have a positive and negative answer.
Mm-hmm.
And that'll be one way that we could represent our answer, right?
Yep.
Okay. So let's take a look at some other things that we have going on. So that's completing the squares. We could also look at some things that are absolute value.
Okay.
And in this case, we're given the absolute value of x minus 4. When you see that, what comes to your mind? What does that mean? What does that look like?
It looks kind of like a V graphically, and it's when it's greater than 8, or no, less than 8.
Okay. Anything else you know about the looks of that function?
It's opening up,
All right. What else?
and it's shifted to the right.
Why?
Because the x minus 4, it moves it. The minus 4 moves it to the right.
Correct.
Yeah.
Okay. So now that we have that in our mind, we have our absolute value function.
Yeah.
And we're supposed to know when that's greater than 8. And so we're looking for our answers there.
Mm-hmm.
Okay. So this guy right here is y equal to x minus 4, right? And we're wanting to know when that guy is bigger than 8, pardon me, less than 8.
Yep.
And then what's this line right here? What's that?
Is it negative x plus 4?
Yeah, so that's going to be the opposite of x. Instead of minus 4, it's going to be plus 4.
Yep.
And we want to know when that thing is going to be less than 8, right?
Mm-hmm. Yep.
So we have that. And we also have this guy to deal with.
Yep.
Okay. So that's one way that we can look at it. Would you have any problems with me switching the signs on this thing and doing it something like this?
No.
Okay.
You just multiplied both sides by -1.
Right.
Yeah.
Okay. So if I add 4 to both sides, I have that for x. But over here, when I'm dealing with this, I would add 4 to both sides. And so now I've found out that x is going to be in between those two conditions, right?
Yep.
-4. So when is this function less than 8? Well, it's over here at -4. And over here at 12. So that's what we have there, right?
Yep.
All right, now what were some of those questions that you had about some other things earlier?
Oh, about factoring polynomials greater than degree 2.
Oh, yeah. Yeah, so let's pass over this guy right here because I'm pretty sure that we can solve that inequality.
Yeah.
As much fun as that might be. And we could also do quadratics, right?
Yeah.
So you can complete the squares with that. You can use the quadratic formula or try to do some clever factoring if that's possible. Okay, so here's the systems of equations. And it looks like we could deal with that by solving for y. That'd be a whole lot of fun.
Yeah.
We can graph them. I'm not going to do that. We're just going to kind of fast forward through this.
Okay.
But if you were to use your graphing calculator and you were to find out what the x value is where they intersect, if you go back onto your home screen and tap x, it'll give you that decimal representation. And if you wanted to know what that fraction was because it was messy, you could tell it on your TI to give you a little fraction answer, and it would then make it 41/14. And then you can use your function notation. Okay, plug that into y1 and see what happens. So anyways, just some stuff that you can do with your graphing calculator if you like that kind of stuff.
Yeah, I've learned a lot about those graphing calculators this semester, like how to program them and stuff to do all kinds of stuff, and how to use like the graphing functions a lot better.
Great.
They're really
So
nice.
what would you do with your graphing calculator with this system of equations? They're not a linear system. It's a quadratic and a linear.
Mm-hmm. I would plug both of those equations in, and just find the intersection points.
All right.
Yes.
We could do that, right?
Yeah.
Or you could set them equal to each other and find out, okay, so we could do a little factoring action, and that would all be great. But anyways. Oh boy, what's this? The vertex form. Okay, so we've talked about the standard form, the expanded form, and now this is the vertex form. And this is one of the reasons why you'd want to know how to complete the squares so that you can put it in vertex form. But you're really not interested in doing that kind of stuff right now because you were wanting something with polynomials, right?
Yeah. Because the last couple times I've taken it, I've seen those types of problems, and then a lot of like calculus type stuff, but just like general calculus, not necessarily a certain field. It's just
okay. So I'm not gonna make you wait any longer. This is what you want: polynomial functions of higher degree. Yay. Okay, so some of the things that we know about polynomials is if it's of the second degree, then it's going to have at most, I said second degree, right? It's
Yep.
going to have at most 1 extrema and at most 2 zeros. So if it's a third degree, a cubic, it's going to have at most 2 local extremas and 3 zeros. Okay, at most.
Yeah.
So that's what we got going on there. And if you know the lead coefficient, it's going to tell you something about where it's going as your x's approaches infinity or negative infinity, right? And so that determines whether the polynomial is even or odd.
Yep.
And I'm assuming that you remember those characteristics about that. So if you were looking at these two cubics, we should know that they're odd degree. And since their lead coefficient's positive, it came from negative infinity and it's going towards positive infinity as x came from the left and is moving towards the right. But anyways, just for fun, you could graph them with certain windows. And you could see as you zoom out, they basically have the same shape, right?
Yep.
Okay. So I'm not going to talk about that. There's a little bit about the end behavior with the lead coefficient being positive or negative and knowing what happens when it's odd or when it's even. Is that familiar?
Yep. Yep.
Okay. Oh boy. Okay. So here's a cubic. You should know that it has a y-intercept of -12. And the end behaviors is that it's, as x tends towards negative infinity, it's going towards negative infinity. And as x tends towards positive infinity, its functional value is going towards positive infinity. And but with the quartic, it's going to have a y-intercept of 35. But it's going towards positive infinity as x, the functional values going towards positive infinity as x is positive, tending towards positive or negative x. Okay, so here's one that would be fun for us to take a look at. Find the zeros to 2x cubed minus 4x squared minus 6. So if that's your function, what are some things that you already know about this thing already?
Well, it's going to have 3 zeros at most.
Those 3 zeros, yes.
It's going to have 2 extremas.
Right. At most, a positive, or probably a maxima and a minima.
Yeah.
What's the y-intercept?
0.
Yeah, it's 0. So on this one, if they're asking us to find the zeros to it, I'll set it equal to 0. And I notice that all of them are even and have a factor of x in it. You okay with that?
Yep.
And I have 2 factors, but the quadratic can be factored again, I believe, right?
Mm-hmm.
And it's what I consider a quick factor.
Yeah.
What are the factors of -3 that sum up to? Okay. So that's going to give us, what, -3 and +1.
Mm-hmm.
And now I set each one of those 3 factors equal to 0. So I have 2x equal to 0, or I have x minus 3 equal to 0, or x plus 1 equal to 0. Okay, so that one's fairly simple.
Yeah, that one wasn't too bad.
And so those are my 3 zeros. And so we could now plot those, and then we could try to figure out a few other things, right? Maybe with some calculus we could find the max and mins, and by taking derivatives, right?
Yeah.
Okay. But at this point, they're just asking us to find the zeros. There's great rejoicing. All right, so hold on. What's going on here? If f is a polynomial function and we have x minus some constant raised to the m power is a factor of f. Okay, so hold on. Multiplicity. Okay, now we have something with multiple roots. Okay, so if something is a 0 and the 0 has multiplicity, the question is, does the polynomial hit the x-axis and bounce up, or does it hit the x-axis and cross through it? Does that make sense?
Yeah.
And the answer to that is, if the multiplicity is odd, it goes through it. But if it's even, it hits the axis and then bounces back. So it doesn't go through it.
Okay.
Does that make sense? Okay. No, it doesn't make sense. So let's do a real easy one. Let's have x minus 0. That quantity is squared. So it hits the x-axis at 0, right?
Mm-hmm.
It's quadratic, and then it bounces up. Does that make sense?
Yeah.
If you have x minus 1 and that quantity is being squared, that's a shift to the
right.
To the right. And what does it do? It hits the x-axis. Does it cross through it? No, it bounces right up. Does that make sense?
Yep.
Okay. However, if you had x minus 1 and that quantity was being raised to the 3rd power, that's just a cubic, right?
Yeah.
And it goes through that 0 and it goes from -infinity to +infinity. So it just goes through there. And anyways, that's what it's trying to tell us with the multiplicity. All right, so I'm gonna kind of move on with that. All right, real zeros of polynomial functions. No, we don't. We want. Oh yeah, we do want real zeros. We don't want anything that's. Oh, okay, so here's one that has multiplicity going on. Okay. So now this polynomial has been factored for us. And what do you know by just looking at f of x equal to the quantity x plus 2 raised to the third power times x minus 1 raised to the second power?
Okay, so it has 3 zeros at -2.
Okay.
And then it goes through that point.
All right.
And then it has 2 zeros at 1, and it just kind of touches it and goes back.
Okay. What degree is this polynomial?
5.
Yes, fifth degree.
Yeah.
So this is a quintic. And what do you know about quintic polynomials?
It's odd.
That's right.
Yeah.
So what's the end behavior?
It's going to go from negative infinity to positive infinity.
Yeah, so, this is what you're going to do with your students. You're going to tell them, take your hands and forget about all the wiggling and squiggling, but show me with your hands what it looks like using both hands.
Yeah.
And, you want them to have their hands in opposite directions, right?
Yeah.
Where it's pointing down, the other one's pointing up.
Mm-hmm.
Okay. So we want it to do something like this, right?
Yeah.
And we have a bunch of wiggle action in here.
Mm-hmm.
And this is where we were talking about it has at most, well, since it's a fifth degree, we know that it has at most 4 humps in it, 4 extremes. And it has at most 5 zeros. So if we're graphing this thing by hand, you've already stated over here at -2, we have a 0. And at +1, we have a 0. But you said it bounced on this one, right?
Yeah, it just touched. Yeah.
And we know that the end behavior is that it's going to go towards positive infinity.
Mm-hmm.
Now, you should also know where it crosses the y-axis.
I don't know.
Okay, so if we were to multiply this thing out, would you agree that it would give us
yeah. Okay.
2 cubed, right? So that's 8.
Yeah.
And when we square this out, that's going to give us a constant of +1.
Yeah.
So this guy right here actually happens to be 0.8.
Yeah.
And this is going to be 1, 0, and this is -2, 0. So we actually know quite a bit about this guy. And so we've graphed it. You happy with that?
Yep.
You got to love polynomials.
Yeah, they're pretty crazy. There's a lot to know about them.
All right, so there we have it. They were a lot of fun. Oh, boy. Dixie Packing Company has contracted to make boxes with a volume of approximately 484 cubic inches. Squares need to be cut from the corners in a 20-inch by 25-inch piece of cardboard. The flaps fold up to make an open box. What size should be cut from the cardboard? So what are they asking for? What are we given?
We're given the dimensions of the box if it was like pressed flat out. And we're given our end volume result whenever we fold it up after we cut the corners out.
Okay. Are you drawing this out?
No, but I can. Let me go get my marker for it.
Now, what you don't know is that this is really fun. This is fun stuff right here. So we want to draw a picture of this. We know that volume is length times width times height. And basically what we want to do is we want to find out what is that length and that width. Because we're cutting out these little corner pieces. Okay, so we have a total volume of 484 cubic inches. Our cardboard is 25 by 20. And we're cutting out these little pieces. Do we know what the length is for those square corners?
Not exactly, but
No, it's a variable, right?
yeah.
Okay, so I'm going to label this as X. Does that make sense?
Okay.
Cutting out X. Now, if I'm cutting out X, the question is, what is this dimension right here?
25 minus X.
Not just minus X, but I've cut it off from this side and that side, so it's 2X. Does that make sense?
Yeah.
Okay, so there we need to make sure that we see that we're actually cutting out two of them, one on each end. Now, what can we say about this distance here?
It's 20 minus 2X.
All right, now we're in the business. Because the volume is then going to be our 20 minus 2x times the quantity 25 minus 2x times our x.
Yeah.
Does that make sense?
Mm-hmm.
So now we have our 484. That's equal to x times all the stuff that I just told you. Okay. Huh. Now what do you want to do?
Solve for X, I guess.
Yeah. That's what I want to do. I'd like to throw this thing into a graphing calculator personally. Right?
Yeah.
Okay, so hold on just a second. I can play with this just a little bit. And I know that this, I could factor out a 2 from this. And so that's going to be 10 minus x. That's going to be 12.5 minus x.
Mm-hmm.
And I also know that cubics have a particular shape. They could look that way, or they could look something like that.
Mm-hmm.
And so we're trying to find out, well, it doesn't make sense. Hold on just a second. It doesn't make sense for this x to be bigger than 10. So it actually needs to be less than 10. Because if this x is 10, then I'm cutting off 10 from both sides, and that's no good.
Yeah.
On the same note, I know it can't be 12 and a half. Well, if it can't be more than 10, it can't be 12 and a half over here. So I know that it has to be between, x has to be bigger than 0 and less than 10.
Yeah.
In order for us to get all of that. So what I would do if I had a graphing calculator with me is I would type that into y1, I'd type this into y2, and I'd find out where it intersects. Does that make sense?
Yeah.
And that would just make my heart happy. There's other things I'm pretty sure you could do, but that would be the one that I would want to do. So you could also type it into your graphing calculator once you had x and the quantity times 20 minus 2x times the quantity 25 minus, and then you could just try to find out what values it would give you. So typing it into your graphing calculator here, you'd have to see that that cutout would be between 1 and 2. Does that make sense?
Yeah.
Oh, and there's another spot that it would work as well. And we kind of expected that that was a possibility, right?
Mm-hmm.
Okay. Oh boy. Is there a parallel between polynomials and long division? Well, yeah. Can we have long division with polynomials?
Oh, yeah.
Oh, yeah. All right. So didn't sound like this was an issue for you the way that you said, oh, yeah. So I'm not going to play around with that with you. But we could have some fun with it. Oh, yeah, we have remainders. Yeah, you could do stuff like that. Yeah. We like it when that divides evenly. That might tell us a little bit about zeros. All right, hold on just a second. Use long division to find the quotient and the remainder.
Oh, that's long.
All right, you have your seatbelt on?
Yep.
Okay, good. You might need it for this one. We're going for a ride. Okay, so when you look at this, this is saying that I have a quartic, right? Polynomial fourth degree, and I'm trying to divide it by a quadratic.
Yep.
Does that make sense?
Mm-hmm.
So what should we get? Well, it makes sense to me that if you have x to the fourth power and we're dividing it by x squared, that we should get something that's going to have an x squared in it.
Yep.
Okay. So here's our long division for it. We ask ourselves, but what would you have to multiply x squared by to get to x to the fourth power? At least that's one way of doing it. And you just say, oh, okay, yeah, I'd have to multiply by 2x squared. And then you multiply the 2x squared times your quadratic, all three terms.
Mm-hmm.
You line them up, and then you subtract them, bring down the remainders, and then you play it all over again?
Yep.
Okay. So it does give you a quadratic, and then it gives you a remainder. Bummer. Okay. So that's no fun. And it does, for all practical purposes, look like a quadratic if you graph it right. And it has a little slanted asymptote or something. As you zoom out, it does look like a stinking quadratic.
Yep.
Okay. So the question is, can we find the remainder if I take the quadratic, 3x squared plus 7x minus 20, and I divide it by x minus 2? x plus 1, and x plus 4. So I can do long division, right?
Mm-hmm.
Now, hold on just a second. If I'm dividing by the linear factor x minus 2, what am I asking? What's another way of saying that?
Is 2 a root?
Right, is 2 a root?
Yeah.
And if I get anything other than 0, then I find out that it's not a root. It doesn't cross the axis at that point, right?
Yeah.
So the remainder is actually going to tell me what the functional value is. So instead of doing long division here, you can just plug in not negative 2 into the function, but positive 2.
Yeah.
And then if we know that x plus 1 is asking what happens when the x value is negative 1, then we can find out what's happening there. All right, so I would use the graphing utility on this one and check those things. So it happens to be that negative 4 is a 0. That was nice. Negative 1 gives us negative 24, and positive 2 gives us 6. So
negative 4 was the only root.
Yeah.
Mm-hmm.
Satisfied with that?
Yep.
You can do the long division, but you could also save yourself a little bit of time.
A lot of time.
Here I'm just using the split view on the 84, where it shows the table and the graph, where I'm tracing the 0.
Wait, you can split screen?
Yes. So when you go into your mode,
Yeah.
down there towards the bottom on the 84, it'll ask you whether you want it horizontal or vertical or full screen. So anyways.
Oh, that is cool.
Okay, so we can find the remainder of this quadratic when we divide by the linear factor x plus 3.
Mm-hmm.
Just by substituting negative 3 into the function itself.
Yeah.
Okay, so here's some things that we need to know are equivalent statements. If x is equal to k, k could be 2 or 4. The solution, it's a root. That means that the function is equal to 0, right? K is a 0 of the function. K is an x-intercept of the graph of y is equal to f of x. And this is what you were already interpreting earlier, that x minus k is a factor of it. And surely if you look at 0.1 and 0.4, you can see that that's going to be the case just by subtracting k from both sides. Oh boy. Can you do synthetic division? You know how to do stuff like that?
Yeah.
Okay, well I'm not going to do that then.
Just take the coefficients and do that little chart deal.
Okay. What's the thing that you have to know? You have to know that if you're dividing by x minus 3, you're going to use not negative 3, but positive 3.
Yeah. And then also if your terms don't stair step down, but in this case they do, then you got to put
So if we're missing any factors, we need to put in their coefficient of 0.
Yeah.
So when you use your synthetic division, you can check yourself with the technology, and if you don't get negative 78, well, you've done something wrong.
Yeah.
So Here we can ask ourselves, okay, does our cubic stair step down like you've said? Yes, we have all of our terms. We have our cubic, our quadratic, our linear, and then our constant. And when we use our synthetic division on this one, we'll use 1, because 1, we're trying to find out if that's the root or not. And, oh boy, it doesn't work, right?
Yep.
Okay, so then that -3 is our remainder. And so we would say that it can be written in the following notion. Satisfied with that?
Yep.
All right, the rational zero theorem. Okay, so we have some polynomial where P and Q have no common integers in common other than 1. Okay. And P is the integer factor of the constant coefficient, and Q is, okay, so our Q is our lead coefficient, right? And our P is our constant.
Yep.
So in this case, we're looking at -9/4 or -2/1. So what are all the factors of -9/4? Well, the factors of 9 are positive and -9, positive and -3, positive -1. And all of those factors could then be over the factors of positive and -4, positive and -2, positive -1. Now, I don't know if you're seeing the significance of this or not. You ready?
Yep.
Okay. So, if this thing has rational roots, then what it's saying is my roots, this is going to be my P, that's going to be my Q, right? If it has any rational roots, it's going to be the factors of P over Q. But in this case, I'm going to have -9. Okay, hold on just a second. So, what are all the factors of 9? So we said earlier, positive -9, positive -3. Okay, and that's all going to be over the roots of 4. Okay. Now, the reason why I chose this particular example to show this is because you actually know the roots of this doodad, don't you?
Yep.
Well, that happens to be what, a difference of squares?
Uh-huh.
Okay. So this is 2x quantity squared minus 3. Okay, yeah, I know how to factor that now. So that gives us 2x minus 3 and 2x plus 3.
Yep.
Okay. So 2x minus 3 is equal to 0, or 2x plus 3 is equal to 0. And we've done the math, and we're going to get 3/2 or -3/2, right?
Yep.
And look, oh, I forgot my 2 up here. Let me hurry up and put that in there. You didn't catch that earlier, did you? I forgot mine.
I caught it. I just didn't say anything.
Oh, thank you. I appreciate that. Spare me the humiliation. Okay, so that's kind of handy. Now, we didn't have to factor it. You could have just, added 9 to both sides, divide by 4, and then take the square root, and you would have got your positive and negative 3/2.
Yeah.
Okay. So this is going to be helpful for you when you're dealing with polynomials. If you're trying to find the roots of a polynomial, the rational roots, you just need to know what the constant term is down here and the lead coefficient, and then you're going to look at all the factors that it would include, right?
Yeah.
Does that make sense? So if you have your graphing calculator, then you can just check your table for those roots.
I can just type in whatever.
Right. So I would look at 9/4 or -9/4. I would look at 9/2 and -9/2. I'd look at 9. Does that make sense?
Yeah, and all the combinations.
And then I would look at 3/4 and -3/4. I would look at 3/2 and -3/2. I'd look at 3. And then I would look at a fourth and -4, a half and a half, and then 1. So outside of that, there aren't any other rational roots according to this theorem. So don't waste your time.
Yeah, that's going to help out a lot, because on some of those problems they would add, or they would say, here's like a quartic polynomial, and here are 2 of the roots. They're complex or whatever.
Yeah.
Are there any rational roots?
Okay.
Something along those lines, and yeah.
So now you're starting to see the light on that. So those don't have to be as foreboding. Okay, so then on this other one where you have x squared minus 2, well, let's see. Hold on. So the only rational roots for that guy are going to be what? The factors of 2 over the factors of 1? So that's positive and negative 2 or positive and negative 1.
Yeah.
But neither one of those work. And of course, you know this one isn't going to work because the roots are the square root of 2. Okay. So just trying to show how that thing is going to work. All right, so based upon the rational root theorem, what are the only things that I can now look for roots on this cubic?
Positive, -1.
That's right. And so then what you want to do is you can just plug in 1 in for x and -1 in for x and find out if it gives you a 0. If it doesn't, it's going to be irrational. You happy with those apples?
Yep.
There's my split screen just for, okay, so now that I have my split screen, I can actually see where it's crossing the axis, right? In between -1 and 0 because it went from negative to positive, and in between 2 and 3 because the functional value went from negative to positive there as well. Did you get that? No rational roots. Man, I worked hard on that one.
It looks like you put some work into this, man.
Okay. So now here we go. We're going to use the rational root theorem. What kind of numbers am I going to look at?
All the factors of 2 and 3.
Right. So I'm going to look at positive and negative 2 over 3. Positive and negative 2 over 1.
Yep.
And I've got a dog in the house. And we got a walker. So we're going to have to do a walker with a big dog.
Yeah, my dog was barking a while ago, and I had to go put her out.
Okay, so according to the rational root theorem, I'm going to look at 1 and 2. I'm going to look at 2/3, 1/3. Anything else that I'm missing? That's it?
Yeah, that's it.
Okay, so then I'm going to look inside my grapher. Oh, I forgot about what? Just -1, +1, -2, and +2.
Mm-hmm.
And that just makes life a whole lot easier when we're looking for those things, right?
Yeah.
So use the technology.
Yeah.
Get used to that calculator that's on there that I showed you at the very beginning.
Yeah.
Get used to how it operates, because they're probably not going to let you bring in your own 84.
No, they won't, unfortunately.
All right, so there were rational roots on this one. Oh boy. The upper and lower bound test for real zeros. Let f be a polynomial function of degree greater than or equal to 1 with a positive lead coefficient. Okay, we're good with that. Now suppose that your polynomial is divided by x minus k using synthetic division. So if it's x minus k, then k is going to be positive. Okay, that's our first condition. K is greater than or equal to 0, and every number in the last line is non-negative. Non-negative, okay. Then k is an upper bound. And if k is less than or equal to 0, and every number in the last line are alternating negatives and positive, then it's a lower bound. Okay. So you'd use your synthetic division here with 5 and -2, and you'd want to see, are all the numbers positive or all the numbers negative, and it would tell you whether it's an upper bound or lower bound on that interval. I don't know if you need to do that, but I thought that'd be a whole lot of fun to see. You okay with all that?
Yep.
Sweet fancy Moses, what's happening here?
Uh-oh, Pascal's.
Okay. How are we going to do this? Okay, so we have Pascal's triangle.
Mm-hmm.
We're going to make some type of funky connection with a lot of mathematics here. And it says expand x plus y all raised to the 5th power completely. You remember doing this?
Mm-hmm.
Oh, so I don't need to do it? Why am I going to use Pascal?
Because it tells you your coefficient, so...
That's right. It tells me my coefficient, so I could run out Pascal's triangle, and I'm going to use 1, 5, 10, 10, 5, 1 for my coefficients, right? And then I could do this for x plus y all raised to the 8th power.
Yep.
Now, let's say that this thing is just awful, just awfully large. Do you know how to find out what those coefficients are without Pascal's triangle?
No.
You don't?
I don't think so.
I have failed you. I have completely failed you as a mathematics instructor.
You probably showed us, and I've just forgotten it.
I may have showed you, but you didn't learn it, and so this is my fault. This is absolutely my fault, and I feel horrible for this. Okay. So I hope this isn't going to be recorded and posted, because if my department chair finds this out, he's probably not going to keep me anymore, because you didn't learn what I have taught, so therefore I didn't teach very well. Okay. Do you have your graphic calculator with you?
Yeah.
Okay. So if you hit the button Math, what menu are you now looking at?
It says math, num, complex probability fraction on across the top, and then
Yeah. I want you to go all the way over there where it says prob.
all right. Okay.
Now what do you see?
Going down the list, we got rand, npr, ncr, exclamation point, random.
All right, I want you to do NCR.
Okay.
Okay. When you choose that, now are you able to plug in numbers here and there?
Mm-hmm. Yep.
Okay. So I want you to do that, and I want you to put 5C1. Now hold on, let's do 5C0. That'd be fun. I just want to see what happens. Let's put 0 in there. What answer did you get?
1.
Oh, you got 1? Okay, hold on. Hit second enter.
Okay.
And change that 0 to a 1.
All right.
What did you get?
5.
Really? Okay, hold on just a second. Hit second enter, and now change that 1 to a 2.
Oh, okay. I'm sniffing it out here.
What are you sniffing?
Okay, so the first number we're plugging in, 5, it's staying the same because that's the total number of coefficients we're going to have, I guess. And then the second number we're plugging in is the like actual coefficient we're on. Like 0 would be our first one. C is going to be our second, or the first is going to be our second. 2 is going to be our third coefficient. It's going to go on and on.
Yeah, so if you hit 5, choose 3, you're going to get 10, right?
Yeah, and then it's going to go count
5,
back down.
choose 4, you're going to end up with 5. And if you do 5, choose 5, you're going to end up with 1.
Yeah.
Okay. This is fun, because we remember Pascal's triangle. We do remember Pascal, don't we?
Yeah.
Okay. So that's it right there. Those are my numbers that we just figured out here, correct?
Mm-hmm.
So if I'm supposed to expand x plus y, that quantity is raised to the 5th power. These are my coefficients. So that gives us 1, x to the 5th power, and then we start declining our exponents. But I have to remember my coefficients. All right, so I ran out of little space, but hopefully you get the picture.
Yeah.
So now if I asked you to expand this guy, and you didn't want to do Pascal's triangle out to the 8th level, now you know what you can use with your calculator, right?
Yeah.
So you do 8 choose 1, pardon me, 8 choose 0. That'd give you your lead coefficient for x to the 8th power. But then you only have to do this halfway through it, correct? Because
then it's going to just count it down.
Okay.
Yeah. Because it's
so hopefully that was good for you.
Yeah.
And My goodness. Now, what were you planning on doing tonight? You were planning on doing some complex roots in the fundamental theorem of algebra. That's what you were planning on doing.
Yep.
You weren't going to do lesson plans. You were going to learn about my favorite subject. All right. What is the fundamental theorem of algebra? Do you know?
No, I don't know it right off the top of my head.
It's fundamental. You have to know this. It's so simple. And it's fun if you don't go mental. All right. So a polynomial function of degree n has n complex zeros. So if it's degree 1, it's going to have 1 complex 0. If it's degree 2, it's going to have 2 complex zeros. Oh, did you see in parentheses that it's also real and non-real? So complex includes just being real as well.
Oh, okay. Yeah.
And notice the second line. Some of these zeros may be repeated.
Yeah.
Okay, so if you have something of the 6th degree, how many complex zeros does it have? It has 6.
Yeah.
Okay. Which also means then that we can factor it over the over the complex roots. And they're not necessarily distinct. So, anyways. So there's linear factorization of these doodads. We're going to have lots of fun with that. Oh yeah, we've seen this. It's not just true with rational roots. It's also true with complex.
Mm-hmm.
Is it all coming back to you?
Yep.
Yeah, we're friends. It's fundamental, right?
Yep.
This is what you like, the fundamental theorem of algebra. Oh, holy sweet fancy Moses. You still have that marker board, don't you?
Yep.
Okay, write the polynomial function in standard form and identify the zeros of the function and the x-intercept on its graph. Holy cow. What's going through your head? I mean, when you look at that first function in blue there, f of x is equal to the quantity x minus 2i times the quantity x plus 2i.
Well, I know I'm going to have some zeros at positive 2i and negative 2i.
Mm-hmm.
And then it's going to be a quadratic.
Okay.
And
does it open up or down?
Up.
Okay. Where's it going to hit the y-axis?
At negative 4i.
How about at negative 4i squared?
Oh, yeah.
Well, what's I squared?
Oh, 1.
Hold on.
Wait, hold on.
All right, so you ready to multiply this booger out?
Yep.
Now, do you make squares? Do you draw lines? You just do it in your head?
I draw lines.
You do stuff like this?
Yeah.
All
Make
right,
sure
so
I get them all.
plus x squared plus 2ix That gives us negative 2ix, and this gives us negative 2I squared. Okay. These two guys.
You
Say that
mean
again?
4i squared?
Yeah, yeah. What did you see?
2i squared?
Don't see 2I squared. What you're going to see is negative 4I squared, okay? Your eyes are deceiving you. Look again.
Oh, there it is.
Yeah, okay. So now that we have that, these two center terms, they are additive inverses, so they disappear. And now what we're left with is x squared. Hold on. That's negative 1 times negative 4, so that's going to be plus 4.
Mm-hmm.
Now, does that make sense?
Yeah. Yeah, because if now when we solve this out, it's going to give us our roots.
Okay. Okay. Now that we have that, so we've seen something like that before. That's great. So the one in blue we know is a quadratic.
Mm-hmm.
This one in red, hold on, that's going to give us a quadratic with those two complex doodads, right?
Yeah.
And then when I multiply it times the quantity x minus 5, I'm going to have a 0 at 5, right?
Mm-hmm.
So that's going to be a cubic with one real root.
Yeah.
What's happening with the fuchsia colored in C?
There's going to be 4 roots, and 2 of them is going to be real at 3. And then the other 2 are going to be complex, one at I and the other one at negative I.
Okay, so when you're looking at C in fuchsia, you also should remember from what we talked about earlier is that it has a double multiplicity there, right? An even multiplicity.
Yep.
So it hits 3 and it bounces.
Yeah.
And we can figure out what those y-intercepts are by multiplying all of our different k's times each other,
Mm-hmm.
if that makes sense.
Yeah.
A conjugate, a complex conjugate.
Ooh.
Do you know anything about conjugates?
Yeah, they're the opposite.
What do you mean they're opposites?
So when you add like a complex number and its conjugate, you get rid of the imaginary part.
We've actually seen conjugates in the last two, or the last slide. Okay. Now, I'm going to back up just a little bit because I can do that.
Okay.
X minus 2i, its conjugate is x plus 2i.
Yeah.
X minus I times the square root of 2, its conjugate is x plus I times the square root of 2.
Yeah.
Those are conjugates. Okay? When you take the square root of something, you remember doing the quadratic formula?
Mm-hmm. Yeah.
There's a plus and a minus, right?
Yeah.
Okay, so the important thing to know is that if you have one complex root, you know its other complex root because they come in pairs.
Yeah.
Namely, they're conjugates. Okay, so did you see that which was shaking? Don't waste my animations on, okay? So if you have a plus bi as a 0, its conjugate is a minus bi. It's also a 0.
Yeah.
Does that make sense?
Yeah.
Okay, so we're to write a polynomial function of minimal degree in standard form with real coefficients whose zeros are 3, 4, and 2 minus I.
Okay. So it's going to be a fourth degree polynomial.
Okay.
And
Anything else you know?
It's going to have x plus 3, x minus 4, and then that's going to be factors of it. And then you got 2 minus I and then 2 plus I, x, 2x.
All right. And then how are we going to find out what that polynomial actually is?
Just multiply all of them together. I guess you could expand it out like that, or just graph it.
Okay. So if you're looking at my marker board here, they told me I have these 3 roots. That one happens to be complex. But if these are the roots, then I can say x is equal to -3,
Mm-hmm.
which means that x plus 3 is equal to 0.
Yeah.
But I can go one step further because I also know that I have x is equal to 2 minus I.
Yeah.
And then I have x minus 2 minus I equal to 0. And earlier we saw that if you have a times b equal to 0, either a is equal to 0 or b is equal to 0. Well, now I've got a bunch of things that are all equal to 0, and I need to multiply them times each other. So you guessed it, I'm going to have x plus 3 times all of this stuff. Okay, so I'm going to grab those 2 linear pairs, those 2 linear factors, and I'm going to multiply them times each other. Is that what you got?
Yep.
X squared minus x minus 12?
Yep.
Holy sweet fancy Moses, do you know how to deal with this other thing over here?
Not really.
Okay.
I guess we just multiply a piece at a time. We're gonna definitely have x squared.
Yeah, this thing, what I want to do is I want to group these 2 guys together and multiply them times each other. And then, because that's going to give me a quadratic, right? And then I can multiply the 2 quadratics times each other and get something to the 4th power?
Yeah.
Okay. So let's see if I can do this. This thing is the same thing as x minus 2 plus I. You okay with that?
Yeah.
And this guy is x minus 2 minus I.
Yeah.
So far, so good?
Yep.
All right. My favorite way to multiply these things to keep things straight. Have I ever done this in my class before?
Yeah.
Okay. Okay. Now, this is going to give us x squared. Super excited about that. You know, I really don't care what happens in here or there. Do you know why?
Because it's going to cancel out.
That's right. They are going to be additive inverses, right?
Yeah.
So the only thing then that really matters is what happens when I multiply these two guys, and they're both negative, so that's going to be positive, right? Okay. So I'm going to end up with a little 4 action, and then a negative 2i, and then a 2i, and then a negative I squared, which I'm subtracting. And does that give me 5 when I add it all up together? So far, so good?
Yep.
Or did I make a mistake?
No, that's it.
That's it? Okay. And now we know how to multiply this out. So that's x to the 4th power minus x to the 3rd minus 12x squared. And then I'm going to have 5x squared minus 5x minus 50, 60. All right, so I add all of that stuff together. I hope you tracked along what I was doing there. So my polynomial is f of x. Oh, there's x to the 4th minus 3x cubed minus 7x squared minus 5x minus 60. And that's my function that has those roots. And that makes sense with this constant down here being negative 60, that those two guys would fit in there. Unless I've made a mistake somewhere along the way.
No, I don't think so.
Okay, so we have to remember that they come in pairs. Ooh, buddy. And then we could do the same thing with this, right? So what degree is this polynomial going to be?
3. No, wait. No. Hold up. 5.
Okay, so 5th degree. How'd you get 5th degree?
Because each of the complex roots will have its conjugate. So, and then there's two different ones. So there's going to be 4 of those, and then we have our just real root. So that's fine.
Right. Yeah, so this is a 5th degree, and we're super excited about that. And then we'd have to get brushed up on our multiplication with complex numbers and know that it comes in conjugates, right?
Yeah.
And so that would give me one quadratic. Once they give me the other root, that gives me another quadratic. So that's a quartic, and then you multiply it times that other linear factor, and that gives us our quintic. So there it is, x to the 5th minus 5x to the 4th plus 15x to the 3rd minus 25x squared plus 24 minus 10.
Yep.
This is what you've been waiting for. Find all the zeros to this polynomial right here. Write it as a linear factorization.
Yep.
So walk me through the problem-solving process to figure this out. What's the first thing that you know, that you think about, that you're starting to look at?
I would try to just do, well, I would try to plug it into my calculator and see if I could then zoom out far enough to where I could see the whole graph and how many turns it makes. And it should have 4 humps. And see,
At most, yeah.
at most. And then and see if I could use the calculator to find all the zeros if it has any.
Okay, so what are the most likely roots that it has? Tell me what numbers I can look at just by looking at it right now, what we've talked about so far.
8, -8, and 4, -4, and then 2, -2.
Right, so I'm going to look at all the factors of 8. Because the lead coefficient is 1, I take -8 and divide it by the lead coefficient, which happens to be 1. So it's really not that big of a deal. So I'm going to look at 8, +8, -8, +4, +2, +1. And if I have some type of graphing calculator, I can do that pretty quickly and check to see if I get any zeros. Once I do that, once I find one of those blessed roots, then I can use synthetic division.
Yeah.
Does that make sense?
Yeah, and then you can make it smaller and smaller.
That's right. So we graph it, and we look at possible roots that, okay, so it looks like what, -2 and +1 work?
Yeah.
Or 0, I don't know, yeah. Are you okay with me skipping over what we just talked about there? But
yeah.
So -2 does work, +1 does work.
Yeah, and then one of those to divide it out. And
okay, so if you're noticing in my graph in red, I have it as linear and quadratic factors. Why? Because my graphing calculator won't allow me to put a complex number in there.
yeah.
You see where it has x² + 1 in there?
Yeah.
Okay, well, that's going to then factor linearly over the complexes as x - I and x + I. So then there's actually 5 factors.
Oh, okay.
Does that make sense?
So yeah. So if it has like complex roots, then it would just show up as like the stage before the
Right.
Yeah.
Yeah.
Okay.
So the other way to talk about the fundamental theorem of algebra is that any polynomial can be written as linear or quadratic factors over the reals.
Yeah.
You can take the quadratic factors out and make them linear if you do it over the complex numbers. So, okay, so when you look at something like this, the first thing that you should be thinking about is the rational root theorem, and then you check those rational roots to see if you can find any linear factors in it, and then look at using synthetic division to break it down even more. Questions? You thinking?
I'm just trying to soak it up.
Okay, so here's a 0 to this quartic. So if you know that's a 0, you also know 1 plus 2i is also a 0. So then you can multiply those two linear factors times each other and get a quadratic and divide the quadratic into this.
Yeah.
Does that make sense?
Yeah, then it'll break it down. And that way you could factor out more if needed.
That's right. Yeah. That's right. So remembering that they come in complex pairs is handy.
Yeah, it's pretty crucial.
All right, every polynomial function with real coefficients can be written as a product of linear factors and irreducible quadratics, each with real coefficients. That's basically what I was just referring to earlier. Okay, so if I'm looking at this guy right here, this quintic, I'm going to look at all the factors of 16 over all the factors of 3.
Yeah.
So I'm going to look at, what, 16, 8, 4, 2, and 1. And then I'm going to put all the numbers and see if any of those guys will work.
Mm-hmm.
So 2/3 is a factor. And once I get that, then I get a quartic, and find out that it breaks down into the following. I'm going to let you take my word on that.
Okay.
Oh boy. Rational functions. Okay, so if we have a rational function, which is a polynomial divided by a polynomial, and if the exponent, pardon me, not the exponent, if the power of the numerator is smaller than the power in the denominator. In other words, you may have something like a linear over a quadratic, or a cubic over something to x to the 6th power, or something like that.
Okay.
That means that the denominator is getting bigger and faster, so it's going to have a horizontal asymptote. Does that make sense?
Yeah.
Okay. Now, if they're equal to each other, then you're going to have a horizontal asymptote, not at y equal to 0, but whatever the lead coefficients of both polynomials for the numerator and denominator reduced down to. And if the power, pardon me, the exponent of the numerator happens to be larger than the one in the denominator, there's not going to be a horizontal asymptote. That thing's going to tend towards positive or negative infinity based upon other.
Yeah.
Where do you have vertical asymptotes? Well, that's when you factor your booger and you find out where the denominator is equal to 0. Because you know when you divide by 0, the universe explodes. So we eliminate it from our domain. And that gives us our vertical asymptote. How about our x-intercepts? Well, the x-intercepts occur when those numerators can factor out to be a 0. Y-intercepts, Well, just plug in 0 for x and find out what happens. Okay, so those are just quick things that you can do for rational functions, just to graph them. And it looks like we're going to have to on tight. Okay, so look at this thing and tell me what you know about it.
Okay, it's going to have vertical asymptotes at positive and negative 3.
All right, because you have a difference of squares in the denominator, right? And it factors.
Yeah.
What else do you know?
It's going to have, or it's not going to have any horizontal asymptotes.
Okay.
Because
you know anything about the end behavior?
It's going to go to positive infinity.
As x tends towards positive?
Yeah.
But what happens as x tends towards negative infinity? The functional value?
It's going to go to negative.
Right, because this is basically a cubic divided by a quadratic, right? Which would give you something that's linear in the end.
Yeah. So
it doesn't divide evenly, but the end behavior acts like a linear. And that's what I just want you to get out of it.
Yeah.
In fact, if you're looking at that graph there, you can see a slanted asymptote.
Yeah.
Why? Because the degree of the two were just one off. And so when you do your division on this, whether it's synthetic or whatever you're doing, it turns out to be linear. Isn't that cool?
That is pretty sweet.
Okay, so this is a linear divided by a quadratic. What's going to happen?
Okay, so it's going to have horizontal asymptotes at oh crap, I forgot. So
Okay.
So if they're equal, it's just the fraction of the coefficients.
Right.
And then if it's if the denominator is greater than the numerator, then it's going to go to positive or negative infinity depending. And then if the bottom is greater than the numerator, or wait, yeah.
Okay, so the denominator in this thing is getting bigger faster than what's in the numerator.
Yeah.
Okay, so this thing, as we tend towards positive or negative infinity, is going towards 0.
Yeah.
Okay. Does the denominator factor?
Yes.
Okay, so that factors into what, x minus 3 and x plus 2?
Yep.
So at 3 and negative 2, we would have our vertical asymptotes.
Yeah.
And it crosses the x-axis, it looks like, at what, 1/6?
Yep.
All right, so there's our fancy graph of that, and we basically nailed that one. The only thing that we didn't do was actually show it broken down into its factors and look at what happens on the intervals to the left and to the right of its zeros. But anyways.
Yeah.
So this one's a quadratic over a quadratic. So its horizontal asymptote is going to be 2. In the denominator, it's a difference of squares. And in the numerator, after you factor out the 2, it's also a difference of squares.
Yeah.
But none of those cancel. So we're going to have some zeros and some vertical asymptotes. If the factors happen to cancel each other, then we would end up with a hole in the graph.
Yeah.
All right, so this is a cubic divided by a linear. It should act like a
quadratic.
A quadratic in the end.
Yeah.
How would you solve this guy?
I'd get common denominators on the left-hand side there.
Okay, so you'd have what, x squared plus 3 all over x?
Mm-hmm.
Okay, that'd be one way to do it.
Yeah.
What's another way?
You could subtract the x over.
Yeah, and then you'd have a hyperbola equal to a linear thing, right?
Yeah.
So you could think of it functionally.
Yeah.
You could multiply both sides of the equations by x and make a quadratic.
Yeah.
Does that make sense?
Yeah.
Okay. On the left-hand side, what you have is a linear plus a hyperbola, and it's equal to a constant.
Mm-hmm.
Just another way of thinking about things. So. And you can just plug and chug numbers in there.
Yeah, it's not very efficient.
But you can.
Yeah, you could.
All right, so here'd be another case where you could multiply both sides of the equation by something.
Yeah.
So you're trying to find out when that linear plus that hyperbola is equal to 0.
Yeah. You can multiply everything by x minus 4. And then go from there.
Yeah. All right, so you could use your graphing utensil to find the intersections. Oh boy. Are you ready to have fun?
Oh yeah.
Okay, so I think this is one that you need to do on your marker board.
Okay.
So I have 2x over x. That thing is going to basically act like 2, right?
Mm-hmm.
In the extremes. And then I'm adding a hyperbola to it, and it has what, a horizontal shift to the right 3?
Yep.
But in the end, it acts like 0.
Mm-hmm.
All right, I don't know if that really helps us any, but then we look on the right side of the equal sign, and that's just a constant divided by a quadratic, so that thing's going to jack squat. Oh, okay, so now we're trying to figure out when these guys are going to intersect. Okay. So how would you solve this?
I have no clue. Maybe start out by factoring the quadratic on the right. And
Does it factor?
Yeah.
Okay, so that's a quick factor. That's nice.
Yeah.
And that factors into, what, x minus 4?
X minus 3.
Oh, x minus 3. Okay. So we'll do x minus 3 and what?
X minus 1.
Oh, x minus 1. Oh, so now that you've done that,
And
Does
then,
that elucidate anything?
yeah, then we can get common denominator on the left-hand side there.
Okay.
And then, so multiply the fraction with the 2x by x minus 3, and then multiply the other one by x minus 1. That way
Okay, so we're at this point right here, and now we need to multiply by our common denominator. And it just happens to be that what's on the right-hand side, its denominator is what's common, right?
yeah.
Okay. So I can say that this is 2x times x minus 3 plus x minus 1 all equal to 2. And I can just drop the denominator.
Yep.
Is that okay with you?
Yep.
All right, so now this is fun. I mean, we did the hard work. We got the common denominator, and then you can just say, forget about the common denominator now. Oh, is this even fun anymore?
Oh, yeah.
Yeah, this is fun. It ought to be immoral. This is so fun. Okay. Do you know how to factor that?
Yep.
So what are the factors of -6 that sum up to -5?
-6 and +1.
Okay, so we're going to now write that as a substitution as -6x plus 5x. And you understand what I just did there?
Yeah.
And now I group the first two together and factor out what they have in common.
2x.
Now you'll notice there's an x minus 3 in parentheses, and by design I have an x minus 3 on the other side. So this thing factors out to be x minus 3 times the quantity 2x plus 1 equal to 0.
Mm-hmm.
Which tells me x is equal to what, 3 and -1/2?
Yep.
Okay. Now, that's the solution to the quadratic. But those two are not solutions to our original equation. You know why?
Mm-hmm.
All right. I want you to notice that this 3 right here is not one of my solutions to this equation right here. The only answer that we have for this equation right here that makes it 0 is -1/2. Why? Okay.
Oh, because it will give you.
Because the fundamental thing that we never do, the unpardonable sin, is to divide by 0.
Yeah.
Right? The universe will disintegrate if you divide by 0. So if you plug in 3 right there, that's an extraneous solution. And we don't want the universe to explode.
Yeah.
Not on my watch, okay? Not on my watch. So therefore, x equals to -1/2 is the only correct solution. If you would have, put that down on the test, they're going to ding you.
Yeah.
And if you would have checked, you would have found out that there would have been a hole there anyways. So now if you're looking at my graph on the left-hand side, I'm using a functional approach. where the left-hand side of the equation is in one color and the right hand is another, and I'm trying to find out where they intersect and stuff like that. Yeah. Okay, so here's another problem where you would use a common denominator.
Yeah.
And the common denominator happens to be
what the big
x times, x plus 2. But we also know that whatever your solution is in the end, you can't have 0 or -2 be one of your solutions.
Yeah.
Okay. So I'm not going to work this one because I think you get it, right?
Yeah.
Okay, so this guy is factored for us. It's a polynomial. It's a polynomial of 5th degree. So it has at most 5 zeros. Well, we know what the zeros are because it's in factored form, right?
Yeah.
So if you're asked to, kind of graph one of these things and you're not given a graphing calculator, once it's in factored form, then you can put it into intervals. And you're going to look at the interval of -3, -1, and 4. And you're going to look at things to the right and to the left and in between all of that and find out what the functional value is. You remember doing that in calculus?
Yep.
I don't feel like doing inequalities for you.
Okay. That sounds fun to me.
But you could have found the rational roots, right? Look at all the factors of 24 over all the factors of 2.
Mm-hmm.
Yippee. Okay. This is in factored form, and so then you can make your little sign chart to find out what's going to happen to the left and to the right of your asymptotic values. What's its x-intercepts? What are its y-intercepts? And then how is it behaving? So it's going to have a horizontal asymptote where the power in the numerator is x to the first power. In the denominator, it's going to be x to the second.
No, yeah.
Okay, so this thing has a horizontal asymptote at 0.
Mm-hmm.
Has vertical asymptotes at -3 and +1.
Yep.
I'm going to find out, is it positive or negative at other places? And you know what? I'm just about out of gas. Solve this. You don't deserve to pass the Praxis. Just kidding. Just kidding. We got to delete that one. Okay, so this one's already factored for us. And then you do your little sign chart to find out where it all be. Yeah, there you go.
Yeah.
So. All right, so we're about to end this show.
All right.
For how to find the inverse for a 2x2 matrix.
Mm-hmm.
Okay, so if you know how to do that, then you can find the inverse for that.
Yeah.
No one really knows why you want to find the inverse for something like that. Oh, yeah, it's to get back to the identity. Yeah, that's fun.
Yeah.
That's good, clean fun. So, anyways. So remember, you can find that graphing calculator. You remember the website?
It's on that first slide, right?
Yeah, there you go, right there, infinitys.com exams tutorials. And you can watch the little videos on their scientific calculator and all of that. And I'm going to sign off. If that doesn't help you, I'm sorry. That's the best I can do.
It was really good. I learned a lot of tips and tricks just then, or refreshed myself on a lot of them as well. That was awesome.
Well, good. And you'll have to let us know what the results are when you're all. And you said you're taking yours in April, right?
Yeah, April 2nd. That's when it's going to go down.
All right. Have you interviewed for any jobs yet?
So I interviewed at Russellville before spring break. I hadn't heard anything back from that. I think a bunch of the other guys did too. I know Logan, Brett, and Cody and Gabby did, but I don't know if anybody else did.
Okay.
Because we actually all went in there pretty much at the same time and hung out afterwards. So
cool.
yeah, and then I also have an interview coming up at Maumelle High School.
Yeah.
Yeah. I think April 3rd. I think that's what it said. During my prep period there.
Oh, cool.
Yeah.
Well, if you want to go to grad school, just know that I've got a program that just might be for you. We even have GTA positions open. Right?
Yeah, I'm definitely set on doing my master's, just because I want to teach concurrent credit courses.
Yeah. Oh, yeah.
Because I've been doing it all this semester, and it's just a different animal. Like with I guess the students just wanting it because they're in there for a reason. They're smart and they want to learn, and they want to be there, or at least mine do that I have now. And I've had just normal level classes, and it's been a mixed crowd of some people want to be there, some people are there because they have to be, and then some people just don't want to be there. And it's kind of hard to handle all that.
Yeah. Yeah, so you have to figure out how to motivate them, how to provoke them to come to the waters and drink deeply of the vast mathematical joy that there is to have.